talk about the armature reaction and the effect of armature reaction on the performance of DC machine. And simply, we said there are two effects. One effect is demagnetizing effect. It means the total flux in the machine will be reduced, which value of the back EMF, armature voltage, will be less than expect or design for. The second one will be the distortion in the flux itself, that it may cause that the magnetic neutral axis to be shifted and cause sparks. We can calculate the effect by many methods, and today we're going to have numerical example how to calculate the effect of armature reaction and how can we count for it to compensate the loss of the voltage. There are two methods to minimize the effect of armature reaction. These two solutions, one using compensating winding, and that will be fitted on the main pole. If I make it big here, you can see that in this main pole, this shaded region, they have the winding around the pole to produce magnetic field. Please, I mean, I can just disturbing the noise. So that's the main pole. If you look at this field winding, it's wrapped around the pole to produce the magnetic field. But when you look here, there are some extra slots in the pole face. They insert extra winding. That's the compensating winding. So it will produce magnetic field to armature reaction. That's one solution. The second solution that I talked about last time, I said that we use interpole. You see this little thing here? That's like small, very small pole between each two main pole. And that also will work for the armature reaction. There is one will work for demagnetizing and one will adjust the magnetic field axis because of the distortion or the shift happen in the magnetic flux. So these are the two solutions used, and we talk about the equivalent circuit. So now we'll just take one example, numerical example, how can we solve an issue like that. That's the first example. Can you see it? We have a 4-pole DC machine and it has an armature radius. Oh, that's the first example. So we have a machine, and this machine has 4. Armature means the rotor. It's 12.5. Effect length of 25 centimeter. So it's like that. That's the armature. Yes, cylinder, and so we say that that's the length of the, which is the depth, and that's the radius of the armature. Okay. The poles cover 75%. Of course, the poles will be like the stator here has the poles. Let me just sketch one pole here. So there are many poles, and if you have 4 poles, for example, and I make like the front view of the motor, and you have 4 poles, so you can say that you divide it into 4 equal regions, and the pole should cover the whole area here. But when I say 75%, it means if you have 4 poles and you divide the whole circumference of the armature, they said, no, it's not 100%. Never been 100%. So it's 75%. It means not the all 90 degrees here will be covered. Only 75%. So not the whole thing here. So you can say will be covering only portion of it. And this area is not covered. So that's what does it mean 75%. So the pole covers 75% of the armature, and the armature winding consists of 33 coils, and each coil have 7 turns. That simply give you the number of conductors that will be used in the armature in the DC machine, and give you the average flux density, which is B. They said that if the armature is lap wound, we said that there are 2 types of how to wind the winding about the armature. There is lap winding, okay, and wave winding. 2 types, and we explain the difference between both. Okay, so what's required? You give the dimension of the machine, and you give the flux density per pole. That's the most important thing. How to find the armature constant Ka. That's very important. And the constant for every machine has its own constant value Ka. And Ka depends on the dimensions of the DC machine. And why K is important? Because you can find the voltage Aa times omega times phi, and you can find the torque, armature torque, Ka and phi Ia. So Ka in both basically. So it's important to find Ka, the constant. How can you find Ka? We give the equation for Ka. Ka is equal to Z divided by 2A pi. That's the equation for calculating the constant. Z, conductors in the armature, total number of conductors in the armature. A, it's a constant, and this constant depends on the type of the winding that you are using in the armature, lap or wave. Now, in this one, we have lap. So since the kind of winding is lap, A will be equal to the number of poles. In this case, the number of poles equal to 4. 4 poles. What about if we have the other kind, wave? We'll have only 2 constant. Doesn't depend on the number of poles. So that's the first. So simply Ka, the constant of the machine, depends on the dimension, 2 factors. Number 1, the number of the conductors, and Aa, the number of path of the armature wire. In this case, equal 4. Z, how can you find the number of the conductors? Just look for what the information about the number of. Okay, we have here 33. The armature winding consists of 33 coils. So we have coils. Do you remember that we defined the winding, the coils, the turns, right? So we have 33 coils. The armature winding consists, so you have 33 coils. Okay, and each coil have 7 turns. Times the number of turns, 7 turns. And each turn has 2 conductors. So that's the number of conductors per 1 turn. That's 7 turns per coil, and this is the coils per wire. You get the number of the conductor, total number of conductor in the armature. So we multiply that. get 462 conductors. Once you find the number of conductors, and you have a number of paths, so you get AKA easily. AA will be equal Z, which is 462 divided by 2 times A, the number of poles is equal 4 times 5. And you get it 73.53. That's the first requirement. Second requirement, determine the induced armature voltage. So induced armature voltage, it means EA. When armature rotates at 1000 RPM, when omega M is equal 1000. So we'll go for the induced voltage equation, this one. We have omega, we have Ka, but we don't have phi. So how can we find phi? So we'll look for any information helps us find phi. We find that they give the average flux density under each pole. That's good. That's BP, the flux density under each pole. So have armature like that. This is the one pole. So they give us information about the flux density under each pole here. Was given equal to 0.75 Tesla. So write this information. B each pole is equal 0.75 Tesla. But the requirement is not B, phi. What is the relationship between phi, which is the flux, magnetic flux, and B, the flux density? Or when we review the magnetic field, phi, yeah, the relation between phi and B. Times A? Area, yes. That's right. That's equal flux density times area. What area? Yes. A 2 4 pi 4 6. What? 7 10 33 coil. All right. So the number of conductors, right? The what we got 462 is right. Yeah. Divided by 2 4 pi, right? Let me check the formula here. Okay, give me the number. Okay, we have the right formula. So, missing something here. I'm missing the number of poles in the top. B. I'm missing B, number of poles. So we need now to find the flux, and the flux is equal to the flux density times A, the area. What area? What we are calculating now? we try to calculate the flux under each pole. So that's the flux is going to link with the armature winding. So I'm interested only under one pole. So we got to find the area under each pole. That's will give us the flux per pole. How we can find that, the area, how we find the area, they give us information in the beginning. If you remember, they give us the radius of the armature and they give us the length. So if you don't want to find the area of the whole cylinder, of the whole rotor, you only find the area under one pole. So if you have 4 poles, we are going to divide the whole area by 4, right? How can you find the area of a cylinder? You find the area of a cylinder if you have, this is the radius and that's the length. Imagine if you spread the sheet, it will give you the area of the cylinder, all right? With the sheet. And when you spread the sheet, the length of the sheet will be like the circumference of the circle will be equal to 2 pi r. And this length of the depth, call it L, for example. So that will be the area of the whole rotor for the armature. But I'm not interested in the whole area. I'm interested only in the area under each pole. And I have 4 poles. So I will divide this area by 4. So the total area will be equal to pi r, right, times L. That's the area of a rectangle. Then I divide it by 4. So it will divide this area into 4 equal regions. Supposedly each pole covering this area. But in this problem, they didn't say that each pole covering 100% of it, and practically never will cover all of it. Some area will be like gaps between each pole and the adjacent one. So this is 75%. So I'm going to multiply that by 0.75. It will give me exactly the area under each pole. So that's the area under each pole. So do you understand that? Yes.
I have a question.
It depends on the type of the winding used to put the armature wind. There are 2 types, lap and wave. The lap, they make it the number of parallel path, the number of parallel path in this row equal to the number of poles. The other one, they make it only 2, because there is one used for high current and the other one used for high voltage. So that will be the area under each pole. So will be 0.75 times 2 times pi. The radius was given equal to 12.5 centimeter divided by 100 to be meter. The length, it's equal to 25 centimeter divided by 100. And the all divided by 4 poles. That's the number of poles. So if we like to have this formula like general used anywhere, so that's the number of poles. And that's the percentage that useful. It depends on the machine. Some the 80%, 90%, 0.75%. And we calculate the area. When I did that is equal 36.8 times 10 negative 3 meters square. So that will be the area. We found the area and the flux density was given 0.75. So it's easy now to find the flux under each pole will be equal to the flux density, which equal 0.75 Tesla times 36.8 10 negative 3 meters square. We get the flux, which is equal to 0.0276 Weber. That's the flux. Once you found the flux, the equation now have the flux, we have the constant K and omega m, the mechanical speed is given 1000 RPM. So we'll go ahead and find omega m, because actually this is revolution per minute So we have to convert it to radian per second. So you can call this n, the speed n. So omega is equal pi n divided by 30. That's the way to get the angular speed. Pi times 1000 RPM divided by 30, you get the omega m. And then substitute by this value in the equation of the induced EMF. That will have Ka phi omega m. Ka, we got it 73.53 times the flux, we just did it 0.0276 Weber, times the speed pi times 1000 divided by 30. We get the induced EMF, which is equal to 212.5 voltage. So that will be the voltage. It's direct substitution. So determine the current in the coil and the electromagnetic torque developed when the armature current is 400 amp. So now we have the current is equal to 400. So you want to find the current in the coil. In the coil. So what's 400? 400 is the total armature current. So say that IA, the armature current given 400 amp. If you want to find in the coil, so you got to know the way or the type of winding. Is it lap or wave? If it's lap, so the coils will be divided into the number of poles parallel path. So you have 4 of them. So this current, which is 400 amp, will be divided among 4 branches. If it was wave winding, so you're going only divided by 2. So in this case, we know that A is equal, P is equal 4. So the current in the coil, one coil, will be equal the total current divided by A in general. In this case, 400 divided by 4, so you will have 100 amp in each coil. The second part of this question, they want to find the torque. It's easy, it's Ka times phi times Ia. We got Ka 73.53 times the flux. We also calculate that's equal 0.76, and the current is given. Of course, you use the total armature current, 400. It will give you the torque, 811.8 Newton meter. So that's how we calculate the important values for the machine. The induced EMF, the armature torque that produced at the armature, and yes.
Is this supposed to be?
IA divided by, oh yes, by 4, yes. By 4, yes, I divide by 4.
Oh,
that's A, that's A.
oh,
The number of bath, that's here, that's A. All right. Yes. Which 30 you're talking about? This one? All right. As you know, that omega in general in electric system, it's 2 pi f, right? But remember, the frequency is cycle per second. Now I'm using this equation, but with n, revolution per minute. So how we convert revolution per minute to revolution per second? You divide it by, okay. So you have 2 pi and then n, you divide it by 60 to make it per second. And then the 2 cancel with the 60 will be 30. Oh, no, 30 was the number of coils. Yeah. Oh, thank you very much. Any more question? Right. I will leave you, there is a second part of this problem that use the other type of winding, which is the wave. It will be just leave it really as exercise, and I'll give you the final answer to it. Okay. Any question on this one? It's easy, simple. Okay. Now let's go for the one that deal with armature reaction. Okay. So there is load. The field voltage, the voltage that we applied across the field winding, because it's separate. And NF, it's the number of turns of the field. That's the rotational loss. PR rotational loss is equal to 10 kilowatts. So we're going to agree about this notation. P power, and you have to distinguish between P power and P number of poles. Usually we are going to use small p for the number of poles. Just we agree about that. And capital P, that's for power in general. So when we use PR, that's the rotational loss, mechanical loss. And negative motive force due to armature reaction is 25% of the armature current. And I want to say something about that. The demagnetizing effect due to armature reaction can be expressed in sometimes you want to make it easy. You said, okay, the effect is equivalent to 0.6 amp in the field current or 0.5 amp in the field current. That's easy. What does it mean, the effect of the demagnetizing 0.5 amp in the field current? It means if you are applying field current 2 amp, actually is not 2 amp, it's 1.5 amp. That will be easy to calculate. But this one, it's more practical. It said that the demagnetizing effect due to armature reaction is 25% of the armature current, not from the field current. So I got to transfer this effect to the field. So put that in our mind. Because the effect in reaction, the effect on the field, on the other circuit, on the field. So I got to transfer this effect from the armature side to the field side. It's magnetization, and the magnetization curve is given. And we said before last lecture, it gives you the relationship between the field current and the induced EMF. So if you want to find EA at any field current, just go for this curve. Okay. The first one, determine the induced EMF at full load. At full load, the machine has the full load, and we need to find the induced EMF. Means find EA. Want to find this value. It's easy if there is no armature reaction. Very easy problem. Well, let's see how we solve this. Separately excited, so it's better always to have a simple sketch for separately excited DC generator. That's the armature side, and that's RA, and that's the current IA. Of course, IA, it comes here, but it's in series, so the same thing. And supposedly there will be a load here connected, because it said that's connected at rate load. And you have here the field, and the field, usually we have rheostat connected to it, RFC, and that's, and that's the source of the field. It was given. The field, and this problem was given, VF was given equal to 120 voltage, and the number of turns of the field for each pole was given 500 turns. And the information given here, the rated value, 240 kilowatt, 240, that's all rated. Number of poles is equal 6 poles, and 600 RPM, that's also the nominal speed. The armature RA, it's given 0.01 ohm. What else? Yeah, the effect of the armature reaction, let's say armature reaction effect, equivalent to 25% of the current in the armature. That's what was said, given. I'm trying to write in a symbol so I know how solve or tackle this problem. Rated current, rated voltage. So the rated voltage, so I have to have the rated voltage here. What the rated voltage here? It said 240 volts. And let's agree about when I say 240 volts, that's the terminal voltage, VT. There is difference between VT and EA. EA is the armature voltage or reduced EMF. VT, the terminal voltage outside. And always in the generator, the current is coming out from EA towards VT. When we have motor next week, we'll have in the reverse direction. Okay. So that's all information given. So first, I want to find the current of the armature, because I have everything. I have 240 volt and also rated load. It means I'm using the 240 kilowatt. So I have here 240 kilowatt. It's given. So I can find the current. How you find the current? We know that the power, it's all resistive, no inductance, anything like that. So the power is equal V term, the terminal power or output power, you can say, let me write it nicely. The output power is equal to the terminal voltage times the current at the terminal. So just to make it in general, that should be I terminal here. But in this case, I terminal is the same as IA. So, and the V terminal is the rated value, 240 voltage times I terminal. And the power is equal to 240 kilowatt. In this equation, I can find the terminal current, the current at the load. So sometimes we call it IL. So you have I terminal equal to 240,000 divided by 240. So we'll get 1,000 N. And since the armature current is equal to the terminal current, I can write now that the armature current is equal to I, the terminal current, which is equal to 1,000 N. So I got the current. If I don't have any armature reaction, it's very easy to find EA. How you find EA in this case? You have the voltage, you have the current, you have the resistance, you just subtract to get the EA. It's a circuit. Let me look at the circuit here. I will sketch it back again. You have VT, and you have resistance, and the current in this direction. So the drop volt should be here, 0.02 ohm, and the current is equal I 1,000 M, and you have EA. So you can write that V terminal is equal EA minus IA RA, or you can say EA is equal to V terminal plus RA IA. And the terminal voltage is equal to 240 volt, and the resistance is given 0.02 ohm, and the current, armature current we found is equal to 1000 amp. So in this case, I can find the voltage, the induced voltage, which is equal to 250 volts. That's EA. You have any question on that? Yes. 0.021. 1, I'm sorry, yes. No, 1. This is a very simple circuit. It's not hard at all. So that's the induced EMF. I have to have it so I can have 240. I cannot get less than that. The current will be 1000 amp. The drop across 0.01 ohm. There is no way. All right, so we'll go for we got the first part. We got the induced EMF. Let's go back to the question here. We got this one, induced EMF. The power developed. The power developed. I want you to get used to the terminology used in with DC generator or any machine. That's developed at the armature. Motor generator, everything generated at the armature, at the rotor. As the armature. When we have motor, the torque will be developed at the armature also. So how can we find the developed power? So since we define it already, it's at the armature. So it's very simple. You just multiply EA, that's here, that's the armature. And the current in EIA. So the developed power, and sometimes you call it armature power, same thing, is equal EA IA. That's pure before before any loss in the armature resistance. So that we have 250 volt times the 1000, we get 250 kilowatt. So this is the pure power produced by the machine before any loss. We're supposed to use it. But we have now two kinds of loss. The first loss, that's the armature, I square R, copper loss in this armature. So that's why we're not going to get the oil power. You can do that. You see, if you see that the copper loss in the armature, how you can calculate IA square times RA. And the current is equal 1000 square, and this equal 0.1 ohm. So what you get? A 10 kilowatt. Yes, 10,000 kilowatt. And that's why if you subtract this copper loss from the developed power, you get the output power. If you subtract them, 250 minus 10, you get 240, which you are using at the terminal of the DC machine. All right. Let's now go to C. So we got the developed power, or the power developed in the machine, the torque developed. How you find the developed torque? Or how you find the torque developed at the armature? Just to know it's developed at the, as I said, at the armature. The same power, you got to use it to calculate the torque. How can you calculate the torque using the power? The relation between power and torque, because you have the electric power equal mechanical power at this. There is no loss. Well, I'm not going to calculate any loss. It's zero mechanical power. What's the relation between power and torque? Yes, torque. The power is equal torque times omega. It's omega m. If you are talking about developed power, it's the developed torque. So the torque at the will be equal to the power divided by omega, which is equal to 250 divided by omega m, 600 RPM. 600 RPM, so you do the equation 100 times 600 over 30. I give you the omega RPM. That would be equal to 7 Newton. To have the calculation for the omega m, here you go. 100 divided by 30, it's equal to 20 pi radian per second. So we did the torque. It's easy. Relationship. That's torque. The torque developed. The applied torque. Applied torque. What's the difference between applied torque and developed torque? The torque at the armature. Now, to find the applied torque, you got to know what the machine you are dealing with. It's a generator. So generator, you apply the torque. There's a prime mover moving the shaft. So if you have, this is the armature, and this is the shaft, and that's the prime mover, whatever kind of prime mover that's rotating the shaft. So this is the power of the prime mover, and it will go there. You will have the developed power in the armature. So there is kind of loss between the two things. You applied some kind of power to the shaft, some kind of loss. It's a mechanical loss, rotational loss. So if you apply some kind of input power, and the input power to the generator is mechanical, so the first thing will drop the rotational, and what's left, the developed. And the developed, that's rotational, and that will be the developed, or the power at the armature. And then you will not get all of it. Then we'll have copper loss. Then you get the output power to the load. So we have two kind of loss. But they ask for the applied torque. So to get the applied torque, I got to calculate the input. And the input in this case, I have the developed, and I have the rotational was given in the problem. When I add the developed is equal to 3978.87. And the rotational loss was given as, I think, 10 kilowatts. Yes, rotational loss is equal to 10 kilowatts. So I add 10 kilowatts, and I get 988.87 watt. That's the input mechanical power. That's the input to the machine from the turbine or the prime mover. But they ask about the torque applied. Well, yes. So, I'm sorry, that's the torque. Oh, okay. That should be the power. What is that? What's the power here? 250. 250. Thank you. 250,000. So, and you have 10,000. $260,000 watt. 60 kilowatt. That's the input. So if this is the input coming here from the prime mover, and the speed is the same. So the speed, because the shaft, they are coupled with the prime mover. So in this case, I can find the torque using the same equation, and that would be the applied torque. Will be the input power divided by the same speed that we got before. So you have 260 kilowatt, and the angular speed we did it before is equal to 20 pi. And we get the applied torque, which is equal to 41,000, no, 4,138. That would be the torque, applied torque, from the prime move. At this point, we don't have any problem, just very normal problem or calculating the all unknowns. We didn't include armature reaction. This coming question is really that's the most important one. We finish all this. That's also important, but torque developed, applied torque. Okay, the efficiency. To calculate the efficiency. But before I calculate the efficiency, I want to include now the effect of armature reaction. Because almost we did all calculation, but without including the armature reaction. We want to know what is the effect. Remember that we calculated the induced EMF or the armature voltage required to get the terminal voltage for the load. To get 240 voltage at the load, the machine or the generator to produce 250 volts. So how I do that? I go to the field circuit here and I try to find the current, the field current that will give me 250. So if you go there, that's the curve. That's the magnetization curve. It gives the relationship between IF and EA. And you need, from EA, you need 250. So you go for 250, that's 240. Let's say that's 250. And then you go down and you look for the M. And that should be the field current that will produce 250 volts required. When I did that on a scale, that current was about 2.5 amp. So say that to find the field current, I go to the magnetization curve and I go for 250 down. I found is equal to 2.5 amp. So I'll say IF is equal to 2.5 amp. But the question is, find 2.5 amp if we don't have armature reaction. But because there is current, I can get 250 at no load, and you measure it in the lab, you find 250. That's no problem. But once you start to attach load to the output of the generator and current start to flow in it, and this current will produce magnetic field, and magnetic field are going to affect the main magnetic field from the field circuit, and then it will drop. The flux of the field will drop, and will drop. The voltage will drop. Will not be 250. Maybe it will be 245. Something. Here they said the effect is 25. If I go back to the problem here, it's 25% of the armature current. So, but this is in the armature circuit. Okay. So you know the armature current IA is equal in our case 1000 amp, right? So what is the effect of armature current? 25%. So you can just say this delta IA, the effect of the armature, 25%, 0.25 times 1000. That will be equal to How many M? So that's 250. That's the armature reaction effect. The armature reaction effect, it doesn't mean N now. That means ampere turn per pole. That's the ampere turn per pole. So I have to take this one and refer it to the field, because this is according to the armature. I want to refer it to the field. But let's first understand something. We said that the field current was 2.5 amp. That's supposed to give me 250 voltage. Remember that the number of turns in the field was given 500 turns. So what is MMF for this current to produce the right voltage? It's the current times the number of turns. That's how we get MMF in I, which is equal to 2.5 times 500. It will give you the magnetomotive force required to produce this voltage 250. That will be equal to 1250 ampere turns per pole. I got the amount. If I don't have armature reaction, this is the amount of magnetomotive force that will produce the magnetic field required to produce 250. On the other hand, I have 250 armature reaction effect that will reduce this amount. But the question is, I want to know now how much magnetomotive force to avoid this demagnetization effect. Simply, I will get this will be decreasing this value. So I will add it. I will say the total MMF to avoid the demagnetization effect, 1250 plus 250. And that's what I'm going to get, 1500. So what does it mean? It means instead of producing 12, of this armature reaction, because the armature reaction reducing by amount equal to 50. How I got this number? It was given that 25% armature current, this is the effect. So now the total MF, it should be 1500. That's MMF. Now I want to find the right current. What I do, MF is equal NI. So I get IF, the new value. I divided this one by the number of turns. I get 3 amp. So what does it mean? It means instead of applying 2.5 amp at the field, no, I apply 3 amp. Why? To avoid or compensate for the effect of the armature reaction. So that will be the new amp that I'm supposed to use. How I calculate it? I find the armature reaction, the effect. It was given 25% of the armature reaction, but to make it fair, I convert everything to MMF, magnetomotive force, NI. Why I'm doing that? Because simply I have number of turns of the field different than the number of turns, I'm sure, in the armature winding. So I got to refer everything to MMF. And once I include it, then I divide it by the number of turns of the field. It gave me IF new. So you can say, what is the effect in terms of field current of the armature reaction? 3 minus 0.25, 2.5, 0.5 M. So the effect of demagnetization is equal to 0.5 M. So that will be the new current supposed to be used instead of 2.5 amp. So that's how the way to calculate it.